Okay, shall we try? All right, so off we go again. Sorry for that. I'll skip the very first intro. We go to the first slide immediately on the social tipping points, which I just referred to the United Nations General Assembly Week. And then the next slide is a bit of the evidence behind why we can speak of the possibility of a social tipping point. And what you see here is the astonishingly high percentage of Swedes who trust in science and who are convinced that science is correct in its assessment that humans are the main cause of climate change. Now, when I lecture about this around the world, I often get the answer that, well, but you Swedes, you're so well informed and you're always well ahead and we admire your work on environment, you're actually a leading country. The number is equally high in the UK and in Germany, but through a foundation called the Global Challenges Foundation, therefore I took the initiative to do a Gallup in China, in India, in the US, Brazil, South Africa, to check what the numbers are. So just as a starting point, as an evidence why we are potentially in a positive tipping point towards global sustainable development, the question to you is, what do you think the level is in countries like China, India, and Brazil? Sorry for the Swedish spelling here. Well, you see, the astonishing results came a few weeks back, and if you look at these numbers, you will barely believe them. In fact, the level in China is 96%, India 92%, Brazil 91%, and US very high, I would argue, 66%. So this just shows that the political leadership in the world has a mandate to act. It wasn't a coincidence that there were 400,000 people in the streets of Manhattan. It's not a coincidence that citizens around the world are deeply concerned, but there's an enormous mismatch between the way how media portrays global environmental risks and the way political leadership therefore responds. But this is, I think, very hopeful, and why there is an enormous need now to have science-based policymaking on sustainable development in a world which is in an entirely new juncture. And that is what this lecture is about. My belief that science actually informs in a very positive way why we had so many people on the streets, and the recognition that there is embedded in societies a very high degree of concern with regards to climate and environmental change. And this is just a slide showing the data behind, which is, a very robust survey just finalized. Now, why do we have this high degree of trust? And here comes then the risk story. What's the update from science? Well, the first conclusion, and I would argue the most dramatic message from science to any leader or business leader or citizen on Earth, is that we now, on empirical observations, can say that we've entered the Anthropocene, a new geological era, where we humans, anthros, have become the major driver of change at the planetary scale. This is extremely dramatic. It's just occurred over the past 20 years. In fact, we know that the branch point is probably post-1989, when we humans exceed the geological forces of change that have been pushing gradually the Earth system, the planet, in and out of glacial periods, for example, in the billions of years of Earth's history. To my students, and you're certainly in that category, and I'm really honored to have this opportunity to lecture with you today, I often try to remind that now, whether we like it or not, we need to navigate and recognize that we're navigating a 369 world. And this is the numbers I used just half a year back, that we are on average moving towards 3 degrees Celsius warming, that we are in the 6th mass extinction of species on the planet, the first to be caused by another species, and that we're committed to 9 billion people in 2050. But just the last month, I've had to revise these numbers, that in fact, the magic code for the coming 2 generations is actually to navigate a 4-6-10 world. We're actually on average moving towards 4 degrees warming Celsius, and we are actually on average committing ourselves to 10 billion people. This is the reality we're in, and this is a completely new situation we're facing. Business is increasingly understanding this. This is a very messy graph. You may recognize it. It's the World Economic Forum's annual global risk report, where they interview some 2,500 CEOs of leading companies to ask them how do they perceive the largest risks to their companies. And of course, you see there issues around governance failures, regulatory failures, fiscal crisis, illicit trade, organized crime, etc. But look at the big red rhombs here, which are identified by CEOs as threat to business stability in the world, to the stability of the world economy. And you see migration, food security, water security, climate change, air pollution, flooding, storms, cyclones, biodiversity loss, the risk of pandemics, infectious diseases, the recognition that we are today, in Thomas Friedman's words, famous columnist in the New York Times, no longer only living in a hyper-connected world, we're living in an interdependent world where well-being and economic growth in one corner of the planet is totally dependent on how we manage biodiversity, land, forest, atmosphere, oceans in other parts of the world. We've reached what John Schellenhuber, the head of the Potsdam Institute for Climate Impact Research, talks of as a saturation point in terms of human pressures on the Earth system. I tried to translate this in very simple words to say we have reached a point where science indicates that we have hit the ceiling of the hardwired biophysical processes that determine our opportunities for economic growth, meaning that now we need to start operating within the confines of a stable Earth system. There's no free space any longer where we simply can just push negative environmental impacts, neither on the atmosphere, nor in the oceans, nor on land. National Geographic quite recently summarized this in a very pedagogic way using the old classic IPAT equation. IPAT for impact equals population times affluence times technology. Now, if you use population, obviously, as one axis here, affluence measured in world GDP as the y-axis, and technology here measured as the number of patents registered. What you see is a time axis through the boxes illustrated in this graph. And the little box in the very core is our footprint in 1900, so that the turn of the last century. And then you see 50 years passes and we barely have a slightly larger footprint. So in 1950 is that slightly larger box. And what that shows is that we actually increase our environmental impacts on the planet in an incremental linear way. In fact, up until 1950, we can say very simply, humanity has very little influence on the planet as a whole. But the entire box is our situation today. We simply explode in our environmental impact at the global scale. And the reason why National Geographic draws junk at the top of this box is not a coincidence, because what's so evident is that what has caused the predominant going to scale of these impacts is not population growth, it's affluence. It's actually our consumption and production of goods and services. So the prime driver over the past 50 years in what has now been called the moment of the great acceleration, which occurs from 1950s onwards, is actually an exponential rise in our extraction of resources. Now, the evidence behind this illustration from National Geographic is a whole series of hockey stick curves. And what you see in the darker brown on the left-hand side is all curves have the same x-axis. It's from 1750 until today. It's from the Industrial Revolution until today. And on the left-hand side, you see the exponential growth of all the social drivers of change, from population growth, GDP growth, to the number of McDonald's restaurants. They all follow the same pattern, as you see. On the right-hand side, in the more yellowish curves, you see the impacts on the Earth system. Now, normally we're only preoccupied in the upper left hand of these, which is the carbon dioxide concentration curve, the classic hockey stick of greenhouse gas emissions. But I can tell you that you can pick any parameter that matters for economic growth and human well-being. They look the same. So what you have here is just a few examples: ozone depletion, extraction of fisheries, emptying fishing resources in our world's oceans, loss of biodiversity, the frequency of floods, eutrophication through nitrogen fluxes, methane release, N2O, nitrous oxide concentrations, deforestation, they all look the same and they all have the same pattern. And this is incredibly important to recognize, that we have this very, very slow pace of impact up until the mid-1950s and this exponential growth from 1950s onwards. Now, why is the reason to be deeply concerned about this? Well, it requires us to look backwards in time. So what you see here is the last 2,000 years of temperature record. And it's a phenomenally important series. It's fantastic that we now can actually, with a very high degree of precision, track back living conditions on Earth, actually 1 million years, but here is the most recent 2,000 years. And what you see here is that temperatures, despite incredible variability in weather patterns, actually oscillate around a very, very narrow band of plus minus 1 degree right through this entire period, up until the Industrial Revolution, where you see the red line starting an unprecedented rise in temperatures, which has now reached in the order of 0.8 degrees Celsius over the past 50 years. And what happens is, when you look at the future, is the following. Bang, you see our 4-degree trajectory over the next century. So it just shows you that the great acceleration and the going to scale from the mid-1950s onwards is not a small thing. In fact, when we say we're in the Anthropocene, we're saying that humanity is now a force able to push the planet outside of its equilibrium. We're actually able to see the risk, the real risk, of 7, soon to be 10 billion people multiplied by our industrial metabolism, jeopardizing, putting at risk the entire stability of the planetary system. So this is a completely new challenge for humanity. I mean, we've had real reasons to be concerned with regards to environmental change for the past 200, 300, even 500 years, but it's always been more or less localized or regional environmental impacts, but never have we had to consider the risk of even jeopardizing the very stability of the big biomes in the world, from the rainforest, the ice sheets, sea level rise, temperatures, the hydrological cycle, etc. Now, this is tightly coupled to understanding risk. So what I showed you earlier is that we on average are moving outside of the planet's equilibrium. We're on average moving towards an average risk of 4 degrees warming Celsius over the next century. But you need to also recognize what is the probability of really low probability but incredibly high impact outcomes. And I just want to give you this data because it is important to couple to our tendency to always focus on averages. So today, we know in 2014, believe it or not, we will be reaching 450 ppm in concentration of all greenhouse gases. So 400 ppm for carbon dioxide, 50 ppm for the other greenhouse gases. Now, as you all know, the United Nations Intergovernmental Panel on Climate Change released its 5th report in September 2014. And it is the best up-to-date science on climate risk we have. It's actually quite a conservative analysis because it doesn't include the risk of major tipping points, and I'll come back to that. But it has done a probability assessment of climate sensitivity using the average of all climate models of significance that we have in the world. Now, we have translated that work into risk. And what you see on this graph is, on the x-axis, average temperature outcomes for the world. And on the y-axis, you see probability of reaching these temperatures at 450 ppm, i.e. the probability of high unacceptable outcomes at the current concentration of greenhouse gases. And what you see here is that the risk of a 4 degrees Celsius world is 7%, and the risk of a 6 degrees Celsius world is 1.6%. Now, let me just tell you that 4 degrees is a place we haven't been for the past 4 or 5 million years. It's a future that I would argue the majority of scientists would call disastrous. It is unclear if we at all could produce food for a world population of 9 billion people at 4 degrees. In fact, we're most likely to have 2, 3, 4 meters sea level rise at that juncture. But I've chosen to focus now in this lecture at 6 degrees. Why? Because 6 degrees is such an improbably catastrophic high average temperature that even the most die-hard climate denialist would agree that it's an unacceptable outcome for humanity. So I would argue that every citizen on this planet would agree that 6 degrees is utterly, utterly unacceptable. Okay, so that's a good number in a way if you want to, carry your argument home, if you sit some time arguing with some climate skeptics. Now, the probability for 6 degrees at current concentration of greenhouse gases is 1.6%. Now, is 1.6% acceptable as a probability for something which is totally, ethically, morally, practically unacceptable? Well, let me compare that with other unacceptable disasters. Accepting 1.6% probability of a 6% outcome, 6-degree outcome, is the equivalent of accepting 1,500 aircrafts crashing every day. Every day. So it tells us that this is a probability level for a catastrophic outcome which we in any other sector of society never ever would accept. But for some odd reason, we do accept it for climate change, which is of course because it's a creeping, slow moving target where we never talk about the low probability disastrous outcome type risk. But we've come to a point for the first time now in 2014 where we need to consider exactly this risk. And this is, I would argue, one reason why we're starting to see so many business leaders, reinsurance companies getting really nervous, because this is starting to actually become recognized that we are at a concentration of greenhouse gases with potentially too high probabilities of unacceptable outcomes. Now, we all know who work in development that the reason for concern in the immediate is how it hits on livelihoods. And this is just one way of summarizing that. This is, I would argue, the most important immediate impact, which is how climate change undermines freshwater supply in the world. This is a fantastic paper. I really recommend it. It's an effort of trying to combine all the leading global hydrological models with the leading climate models and do an average ensemble analysis of what are the risks at 2 degrees Celsius warming, meaning the warming that we are unfortunately very likely to end up with, even if we are quite successful in diminishing our emissions of greenhouse gases in the very short term. And what you see here in red are the regions in the world projected to have 25% or more, 25% or more reduction of rainfall at 2 degrees. And what's important here is to see the US, which is experiencing right now the worst ever registered drought in the San Joaquin Valley in California, the droughts you've been experiencing in Texas, which are actually in line with the science. And look at Latin America, the risks of even the Amazon rainforest being pushed towards an abrupt shift towards a savanna because of underlying changes in rainfall patterns. But look at Europe, Southern Europe, facing a situation where any agronomist would say, well, if you lose 25-30% of your rainfall, you actually face the real risk of collapse of farming systems, not a reduction in yields, but actually collapse. So this is a world already 2 degrees Celsius. Now, the question then is, which science has been forced to ask over the past 5, 6, 7 years is, are we leaving a desired state for the planet? Is there a real risk of destabilizing the Earth system? And we actually can answer this question by looking at the past. So what you have here is what you've all seen, the 800,000 years of ice core data. This is data from Greenland, and it shows the moving gradually in and out of ice ages. So what you see is the cold -4 degrees Celsius points where we have roughly 70 meters lower sea level on Earth. We have ice capped at levels that takes us down to latitudes which go far, far southern parts of Europe and parts of the US. And then that is with intermittent periods of what we call interglacials, and you see the interglacials coming close to the 0 degrees Celsius line, which are the warm periods where we've seen biomass, where we've seen vegetation growing at a much more prominent level. And what is interesting with this graph is to see how incredibly small the temperature variability is with forming the difference between ice age and non-ice age. And look at the Eemian, which is the last time we had a warm interglacial. It's 120,000 years back. And if you look very carefully, it has roughly 2 degrees or 1 degree warmer than today. And if you look at the 2 degree line here, which is the 2 degree target, which we all discuss in terms of climate policy, you see that that is roughly at the maximum temperature of the Eemian. And the Eemian is a period where we had several thousand years of plus 2 degrees warming. And at that period, we actually had 4 to 6 meters higher sea level. So this is just to tell you that we know with quite high degree of certainty that when temperatures for a long time stay at plus 2 degrees Celsius, we can expect at equilibrium 4 to 6 meters sea level rise. So this is just a reminder that we know quite well how the planet responds to temperature rise. But now let's take another period of this ice core. So it's the same ice core, but it's the last 100,000 years. So this is taking out the last glacial period. And I do this because we've been modern humans on Earth for the past 200,000 years. So this is the entire y-axis here is a period where we've been modern humans on Earth. On the y-axis, you have temperature variability in degrees Celsius. So it's a good proxy of how it was to live on Earth. And what you see is the tremendous jumpy ride humanity had almost throughout the entire glacial period, which took us right through the period of modern humanity on Earth. In fact, the jumps here are incredible. Over periods of just 10 years, we could have plus minus 10 degrees Celsius. There are some cold points, and one of them, the coldest one, you see is roughly at 73,000 years back, is a period with roughly 50, 60 meters lower sea level in the world. And recent analysis show that we were down at only 15,000 fertile adults on Earth at this point. We were stuck hiding in the Ethiopian highlands, one of the few or the only place where we still could find fresh water and some food. So this just shows that we've gone through a tremendously jumpy period where we were only a few million people on Earth on average. We were hunters and gatherers. We had a rough time until we leave the last glacial period and enter what you see in the red circle here, the extraordinarily stable Holocene period. So this is the Holocene interglacial that we've learned in school as our current geological epoch. But now scientists are suggesting that we may have to rename this period to the Anthropocene because we're moving out of it. But look at the stability of the Holocene. It's a period where we have incredibly a variability maximum of plus minus 1 degree Celsius. And that stability has been absolutely decisive for economic growth and world development on Earth. Why? Because we know that we barely enter this Holocene period and we do our most important invention of the entire modern civilization on Earth, namely we invent agriculture. And the interesting thing with this invention is that it occurs simultaneously in at least 4 different places on Earth. And because we know, with certainty that we had no smartphones, email, or SMS abilities at that time, we did not communicate with each other. In fact, we can say with quite high degree of certainty that the reason why we invented agriculture was that rainy seasons become so predictable and stable. Temperatures over periods of at least 100 days became repetitive year after year after year. The savannas, grasslands, rainforest systems, which genetically have existed in their kind of species diversity, often for 100 millions of years, settled in our current ecosystems. So to put it simple, everything that we nurture, everything that we depend on, everything that we love, and what we call nature as we know it, establishes itself in the Holocene. So all the resources, all the ecosystems settle in and stabilize themselves in the Holocene. And this is why we are able to develop the modern civilization as we know it. And we established the Mesopotamian irrigation civilizations, the Maya, the Inca, the Chinese empires, the Roman, the Greek empires. We reached the great acceleration point in the mid-1950s. We're 3 billion people, 10 years after the Second World War. We put in the high gear. We moved towards 7 billion people today, committed to 10 billion people. We're starting to hit the ceiling. But one thing is clear from science, and it's as dramatic as it's simple. The Holocene is the only state of the planet we know that can support the modern world as we know it. We can live outside of the Holocene. We have done that before, but we cannot, there's no evidence at all that we can support economic growth and human well-being for 10 billion people outside of the Holocene. Now, this is, in my mind, the most dramatic game changer in this world, because we've only known this for the past 5, 6, 7 years, which means that we're the first generation to stand on this knowledge. You might fall back and say, my goodness, this is truly a kind of a dark conclusion. I would say it's entirely the reverse. It is really an enormous opportunity because we know the Holocene so well. So we can define, even quantitatively, what are the Earth system processes that regulate the Holocene stability? And can we, for those Earth system processes, even define for control variables that regulate these processes a boundary beyond which we risk moving out of the Holocene? And if we could quantify for all the regulating Earth system processes that determine our ability to stay in the Holocene, quantitative safe boundaries, it would give us a safe operating space. And we can then develop inside that space. Because who wants to play soccer or any kind of sports outside of the game? Someone will blow the whistle and tell you, you know, you're off limits. But here is an opportunity for science, thanks to the fact that we know Holocene so well, to define that safe operating space. And that is the planetary boundary framework. Now, before we come to the framework, though, just to give you a few snapshots of what's happening right now. So, you know, if science tells us we're in the Anthropocene, is that really something to be preoccupied already today? Well, yes. Just a few months back, you know, the scientist's nightmare was published in 2 separate independent research groups showing that a series of glaciers, a series of ice sheets in the West Antarctic ice shelf seem to have crossed the tipping point towards irreversible melting. Now, this is incredible because it occurs already at less than 1 degree Celsius of warming. It occurs on the Antarctic ice shelf that we've always thought to be seen to be resilient. And this is potentially exactly what we don't want to happen, namely that the Earth system takes over irreversible processes. So far, it's we humans kind of triggering changes. And of course, we could then, if we, you know, act early enough, we can change course and avoid damage. But the nightmare is if we trigger changes and then the Earth system itself takes over and starts self-accelerate change, where we humans no longer can play a difference. And what seems to be happening in Antarctica is that a few glaciers have been melting from below through warmer ocean heat. The Antarctic glaciers stand on sloping rock, and they stand on this rock thanks to ice plugs that keep them in place. Now, unfortunately, a few of these ice plugs seem to have now irreversibly gotten out of place, which means that the Thwaites Glacier seems to be sliding out in the ocean. And if the Thwaites Glacier slides into the ocean, it will probably carry with it a whole series of other glaciers as well. And if this is correct, this observation that we may have crossed already today a threshold in West Antarctica, we are in for at least another meter of sea level rise already this century. In fact, we're probably in for another 3 meters over the next 300 years, but 1 meter potentially this century. And that is to be added to the IPCC's average conservative estimate of 1 meter. So, you know, already at 1 degree Celsius warming, we can no longer exclude a 1 + 1 = 2 meter sea level rise this century. So you see that there is a reason to really look at the Holocene as our desired state. This goes also for biodiversity. I was, you know, leading the planetary boundary science. We included, which I'll soon be presenting to you, biodiversity as one of the regulating systems for our desired future on Earth. This was criticized because many said, well, but biodiversity doesn't have tipping points at the planetary scale. We try to explain that that is not necessary. If we lose enough biodiversity and ecosystems start collapsing, if that occurs in many enough places in the world, it becomes a global concern. But this research that came out several years after we published the planetary boundary work in 2009, led by Tony Barnowski and colleagues, shows that even for biodiversity, we may actually have a global tipping point. And they predicted that if we continue losing biodiversity at the current pace, at the mass extinction pace, we're losing biodiversity at 1,000 times faster than natural background rate, we may actually cross a tipping point by mid-century where we lose so much genetic diversity in the biosphere, both on land and in water, that we can no longer depend on ecosystems functioning in a way that they can deliver, clean air, clean fresh water, biomass growth. So this is, another indication that abrupt changes need to be considered also in sustainable development. So to summarize this risk chapter is just to kind of conclude at this point that we are now in 2014 observing two giants colliding, which we did not have before. The first giant is that we're going to scale with the social momentum of growth in the world. We are committed to 10 billion people, 10 billion people, but also remember that it's not the numbers that is critical. The critical issue is that the hockey sticks I showed to you earlier have been predominantly caused by the rich minority in the world, the 1.5 billion people that stepped onto the Industrial Revolution in the mid-18th century. Now, for the first time, we can actually envisage eradicating poverty in the world. We can envisage eradicating hunger. We actually have projections of a 500% growth in economies in developing countries. We envisage a world with 4, 5, 6 billion middle-class citizens by mid-century. This is a phenomenally positive outlook for humanity, that we're going to scale with development in the poorest regions in the world. But this is a right to development that we now need to consider. It's a giant which is waking up right as we speak. We didn't have that before. Paradoxically or a bit cynically, you could say that one reason why we don't have larger problems in the world is the fact that of the inequity in the world. And now we're going towards equity. The other second giant is that for the first time ever, we start seeing the first signs that the Earth system is starting to send invoices back to the economy. This has never occurred before, but Antarctica is showing signs, the Arctic is showing signs, the oceans are showing signs of starting to send feedbacks that can hurt social and economic outcomes for the world and self-accelerate unacceptable change. So that's the juncture we're in. And the question then is, how can we do something about this? How can we adopt and explore an agenda of human development within a safe operating space? And that resulted in the planetary boundary framework. So we asked leading global environmental change scientists the question I posed to you before: if the Holocene is the desired state of the planet, what are the Earth system processes, the environmental processes that regulate the ability to stay in the Holocene? And can we define boundaries within which we have, which is shown here in green, a safe operating space? 9 processes have been identified, and they include the big 3 systems where we have evidence of planetary scale tipping points: the climate system, a stable ocean system, here with the key parameter ocean acidification, and of course, depletion of the stratospheric ozone layer that protects us from dangerous levels of UV radiation. More surprising, perhaps, science today shows that under the hood of the Earth system, a bit kind of hidden from the big agenda, the biosphere is working in our favor. The biogeochemical flows are operating continuously to buffer, dampen, or reinforce the state of the planet. And this includes the global hydrological cycle, how fresh water flows through the biosphere, regulating entirely how much biomass, basically the green stuff on Earth, which regulates, for example, the carbon sinks in the world. Land use change, which is, the strata upon which all living species depend. Biodiversity loss, that regulates the genetic diversity, and how we interfere with the big nitrogen and phosphorus cycles. So these are what we call the slow variables that regulate the resilience on Earth. And then we have included two very human manipulated systems. The first one is aerosol loading, simply put, air pollution, the degree by which we pump out soot, black carbon, sulfates, nitrates, particles in the atmosphere that both can threaten human health at large scale, but also, as proven by the Asian brown cloud, affect entire monsoon systems. So big impacts on large regulatory systems in the Earth system that, for example, in this case, related to rainfall. And finally, chemical pollution, the risk that we humans load the biosphere, the Earth system, with so many organic pollutants, nuclear waste, heavy metals, neonucleotides, etc., that the cocktail effect of that could actually impede permanently, for example, the genetic code of species on Earth. So this is the 9 planetary boundaries that were suggested in 2009, which through the last 5 years have gone through a tremendous journey of scrutiny, which today has led to an update. And I just want to flag to you that it reinforces, if anything, that these 9 are robustly identified. Planetary boundaries, just in 2 short slides, are different, but builds on the great advancements of Earth system science over the past 30 years. It's not limits to growth or carrying capacity or guardrails or tipping elements, because all those concepts in the past did the following. They did try and assess resources, ecosystems, climate stability in the Earth system, but then they also included the human dimension by asking the question, okay, so how many resources do we humans need, and how ingenuine are we in terms of technology, innovations, introductions of different types of resource extraction systems. And then they compare generally how many resources do we have on Earth and how many resources do we actually need to exploit to satisfy human needs. And as soon as human needs exceed planetary supply, we're in an overshoot situation. Now, these have been criticized because we've tended to underestimate the innovation capacity among humans. That's, for example, the criticism of the limits to growth concept. Planetary boundaries does something very different. It actually takes out humanity for a moment and just looks at the planet. It's as if we were standing in space, trying to interview planet Earth and ask Mother Earth, irrespective of humanity, what is it? What does it take for you to remain in the Holocene? And then we identify all the Earth system processes entirely independent of our ability to manage them or influence them. And then we define the boundaries just from the latest Earth system science. And that defines quantitatively science-based boundaries or global sustainability criteria. And then we can put humanity back inside the safe operating space. And then there's nothing hindering us to grow or to not grow, to have equity or to not have equity inside the safe operating space. We make no assumptions on human technology. We make no assumptions on human needs or aspirations. And that's critically important with regards to how this concept is complementary to what has been done before. Each boundary is defined by scanning off the latest science. And incredibly important is, and this is a little bit of a messy graph, but just look at the left-hand, we call this the Rastafari graph of the planetary boundaries. And what you see here is a green area, a yellow area, and a red area. So what we do is we scan off science. And of course, for a boundary, take climate change, there is scientific uncertainty. We don't know, and we'll probably never know exactly where a tipping point is, shown here in the little graded line. So what we do instead is that we scan off science to see where does our current state of knowledge indicate within a range of uncertainty where we start seeing indicators of crossing potentially catastrophic tipping points. And that gives us a range of uncertainty, which we assess for climate to be between 350 and 550 ppm for carbon dioxide. We use carbon dioxide concentration as one control variable. Now, we took one normative stance in this methodology to say we should place the boundary not at the point of the tipping point, not at the point of the upper end of the uncertainty range, which then goes from yellow to red, but rather at the lower end of uncertainty. So we do apply a degree of precaution in the methodology. So the boundary is not the point of the tipping point. It is the point beyond which we enter the yellow area, which we call a danger zone. So anywhere in that danger zone, we may see abrupt changes. And we have great proof that this concept works because we are in the danger zone for climate change at 400 ppm for carbon dioxide, and we start seeing irreversible potential catastrophic changes in Antarctica. So that's how the boundary procedure has gone for all the 9 boundaries. And it's incredibly important for you to recognize that a safe operating space, if you transgress a bound, doesn't mean that the planet collapses. It means we go into a danger zone where probabilities of collapse increase rapidly. Okay, here is work in progress. We are actually updating the planetary boundary framework. It's in review right now. Hopefully you'll get a scientific paper coming out very soon. I just want to share with you that the 9 boundaries stand strong. We're improving the quantifications, but what you see here is that our conclusion is that we're still in a danger zone on climate, on biodiversity, on nitrogen, and in fact also phosphorus. Our first assessment showed that we were in a safe operating space on phosphorus, but it's more robust than ever. Here comes a series of slides I'll be going through very quickly that we're trying to downscale the boundaries to the regional level. So for example, biodiversity, here shown in a map of mean species abundance, where we try to take the global boundary, which we have set at not losing more than 10 species per year, which is 10 times higher than the national background rate. We can then translate that in defining also a regional boundary level as, for example, mean species abundance for different ecosystems. And what you see here is a first assessment of, in red, areas where we actually have transgressed the boundary, yellow in a certain zone, and green in areas where we're in a safe operating space. And that can then be projected into the future, here showing projections to 2050 under business as usual. We're doing the same for freshwater, taking the global boundary, which is set as the maximum allowed consumptive freshwater use of the global hydrological cycle, to define the minimum amount of fresh water we need to keep in all the river basins of the world. So we're twinning the global boundary with the regional boundary. And here again, you see in red indications of basins in the world where we are really in a dire straits, but in other regions we still have degrees of freedom. You can do it for ocean acidification, which shows projections of where we enter a red domain if we continue business as usual. And we even do it for nitrogen, which you see going on the wrong direction. Oh, sorry. Yeah, so here's nitrogen and phosphorus. And just to show you that we can actually now downscale the boundaries to the local level of policy and operational scale. Okay, now coming to a closure then, what does all this mean for the way forward? Well, to begin with, and now I'm at the governance slide, it means that we need to become planetary stewards. We need to combine bottom-up governance management for sustainability with planetary stewards. We simply must recognize that we now need also to define science-based sustainability goals at the global scale in order to create incentives for a transformation to desired development trajectories within a safe operating space. And we've been exploring that scientifically quite a bit to see how that can work. And there's a paper which I refer to here that Victor Galas and others have been looking at, and also a major Earth system governance program that are looking at different ways for Earth system governance. Secondly, we've just published a book on innovation, which also explores, does a safe operating space hamper innovation or enable technology breakthroughs? And we would argue that there's a very strong case to be made that a safe operating space actually could increase the degree of opportunity for innovation, meaning that setting tough planetary regulatory boundaries does not necessarily stop development. It actually raises further the stake for, a very rapid transition towards a decarbonized world, for example. We need to become stewards of the biosphere. Now, why is that? Very briefly, and I think this is no surprise to you, climate interacts with the other boundaries, and land boundary, biodiversity boundary, water boundary, nitrogen, phosphorus boundaries are entirely coupled to the climate boundary. And this is why we need to become stewards of the entire Earth system. This is illustrated here by, I would argue the most important ecosystem service on Earth, the fact that we have emitted, and the number is at the planet here, the little round ball, 545 billion tons of carbon since the Industrial Revolution. Now, we know we've thereby increased atmospheric temperatures by roughly 1 degree Celsius, but it's only half of that amount that remains in the atmosphere, 240 gigatons. But in fact, over half of our emissions are actually absorbed by oceans and land-based ecosystems, which is a fantastic service to our world economy, but also a proof that Earth resilience is working. The Earth system is applying its biophysical processes to try and remain in the Holocene. This is a proof that resilience actually is operating in our favor. The Earth system is our best friend, buffering in an astonishingly effective way half of our emissions. Now, so that's just one way of explaining why we need to take an integrated systems approach to global sustainable development. What are then the most important transitions to move into a safe operating space? I would argue it is three: a global transition to sustainable food systems, a fossil fuel-free world economy by mid-century, and a transition to a circular economy. And I'll be just quickly flipping through that. There's evidence that we actually can succeed in these transformations. The first is we can define sustainable agriculture from a planetary boundary definition. Has never been done before. That we need to produce food now within a climate boundary, a nitrogen boundary, a land boundary, defining quantitatively what we mean with sustainable agriculture. John Foley and colleagues recently, in a paper I was part of, showed that we can feed humanity by closing the yield gap. Unclear still if we can do it within a safe operating space. That remains a research challenge, but it just shows that we can actually succeed in feeding humanity. The Global Energy Assessment recently showed that we can actually transform the world energy system within a 2-degree climate boundary. It will require extraordinary efforts. It will require policies, legally binding climate agreement in Paris, enormous investments in renewable energy, and a fantastic improvement in energy efficiency, but it is possible. And this is of extraordinary importance, not least when we see that we're going to scale on solar and wind. If you wake up in the morning, a Saturday in Germany, the world's 4th largest economy, you're likely to get up to an astonishing 70% of your electricity from solar and wind. So these are examples that things are really happening at the big scale on renewable energy systems. Finally, on the circular economy, the European Union has recently identified that the only way for Europe to be competitive in a saturated world with rising competition from 9 billion people living in increasingly wealthy economies is actually to totally change business models towards circular business models. Scrapping this linear production system where producers hand over ownership to consumers that dump waste on waste piles, and instead closing loops on rare earth metals, nitrogen, phosphorus, all materials into business models where we rather have relationships with businesses where you don't own your laptop, your mobile phone, or your car. You simply have a relationship where the producer maintains its responsibility to recycle the entire set of energy, material, resource flows. And this is quite an exciting agenda where we're seeing more and more evidence that actually works also for the economy. For example, Michelin tires in the world. We have been working with the World Business Council for Sustainable Development, defining a planetary boundary-based Action 2020, where businesses can build in defining global sustainability within their business models. This has been quantified for the climate, land, water, nitrogen, and biodiversity boundaries. It's an incredibly step forward in operationalizing planetary boundaries within business. And there's also explorations of how planetary boundaries can affect the economy. And here I'll actually go past this theory very quickly because I've actually been talking about it. So sorry for the following. And I just want to end with this final slide, which is the work that we've been doing for quite some time now together with the Sustainable Development Solutions Network and then Professor Jeff Sachs at the Earth Institute, of defining the twin objectives of how we can meet human development goals, eradicating poverty and hunger, within the planetary boundaries of a stable Earth system. So to start thinking of the economy developing within a stable Earth system. And there's more and more evidence that this is actually an agenda that the political system is understanding. So I would argue that the proposal of Sustainable Development Goals, which is now on the table from the Open Working Group in the General Assembly of the United Nations, actually has applied planetary boundary thinking in how it defines our common future, defining very aspirational development goals, but also setting a climate goal, an ocean goal, an ecosystem goal, and a freshwater goal, and even locking in food security within a sustainable management of nitrogen and phosphorus. So believe it or not, we're starting to see a discourse of understanding that we now need world development on a stable planet to navigate the Anthropocene. Thank you very much. That was all from my side. Ska jag starta klockan från början? So I'm not sure if you hear me now. I hear nothing from your side, but I guess we should have a Google Hangout Q&A opportunity. So I'm kind of babbling along here to see if you hear me and see if you, Matt, or anyone else is going to kick off a few questions or comments. So silence on our side here in Stockholm.
Probably.
There's like this. So Shiv, Matt, can you hear us? Now I hear you, Shiv.
Okay, great.
Okay, good.
I had some questions in Skype. Very good chat.
Okay, great. So you want me to answer those in chat form or verbally?
Verbally is fine. Maybe 15 minutes worth of question and answer?
Yeah.
Okay, thanks.
That's fine. Okay, so let's have a look at the first. Is this the first question here? Oh, good. Now I'm just bringing up the chat space here. A bit better would be okay. Yeah. Okay, so. Okay, my question is, Nicolas Contreras, if environmental costs of emerging economies in developing countries were internalized, would there be any convergence? Well, you know, there's been some really famous work done by leading economists, not least at the Bayer Institute on Ecological Economics, but also by Sir Partha Gupta and others, showing that when you analyze inclusive wealth, when you try to truly internalize environmental costs, to begin with, GDP growth disappears in essentially all developed countries and in most developing countries as well, but it looks better in developing countries, and a few countries actually remain with positive economic growth. But simply put, if you internalize environmental cost, which is difficult to do, but if you do that, even with conservative numbers, you end up showing very clearly that planet Earth is subsidizing our economic growth. So I think that's actually quite clear. Luisa Lema, I would love Roxanne to give a few quick examples on how the team of co-authors came up with the actual boundaries they define on their paper. That explanation is on a different paper, which students did not have to read. Okay. Yes, well, I would advise you, in fact, if you're interested, to try and get hold. I can send that over to Matt, the Ecology and Society, the long paper that we wrote on planetary boundaries, which has the entire methodology. But I'll give you an example, and I think I'll continue on the climate boundary because it's the most pedagogic one. So what we did was to actually scan through the scientific literature on the scientific evidence around tipping elements or tipping points in the climate system. So we built that on Tim Lenton's very famous tipping elements paper, the synthesis done by John Schellenhuber and colleagues, the indications, in fact, that we have even in the IPCC, but also, research from the Arctic, from Antarctica, coral reef systems, and when we start seeing risks of thresholds. You may have seen the red embers diagram showing and analyzing risk of abrupt changes and translating those to the two control variables that we use. And one control variable then, as I mentioned, is concentration of carbon dioxide. So at what concentration of carbon dioxide do we see evidence? I see I have a problem on the Skype here. Hello. Hi there, hope you're back. So I was saying that for the climate boundary, I'm addressing the question of how we actually went about defining the actual boundaries. So I just focused on how we scanned off the literature on climate science, translating the observations and evidence of tipping points to concentration of greenhouse gases, setting up the entire range of uncertainty, and thereby defining the boundary range. That's one. But I guess your question was rather how do we find the 9? And I can tell you that that wasn't all that difficult because there's been such enormous advancements in Earth system science over just the past 20 years that it's not so difficult to really scan off all the candidates if your question really is what are the Earth system processes, the environmental processes that regulate the Holocene equilibrium of the entire Earth system. And of course, I can tell you that we were playing around with a few additional candidates. I mean, one candidate that continues to preoccupy me is pandemics. Is it so that we could envisage a situation where we get so severe mutations, particularly of viral zoonotic diseases, that it actually could knock out a large portion of the world population, just like the pest did, knocking out half of Europe's entire population in the 15th century, sorry. Now, we didn't include that because we didn't see evidence of that kind of global threat. So we really scanned off in a very, typically scientific, robust way, what are the processes that are involved in regulating the Earth system. Then we put this out for peer review, and it's been out for peer review first in an open wiki-type review at Nature, the journal that published it, with critical reviews from many, many scientists even published in that issue. And then it's been up for scrutiny over the past 5 years. So for example, there's been one suggestion that by Steve Runnings, a very famous professor, that net primary production perhaps should be a candidate for a boundary. Now we explore that very carefully and recognize that net primary production of biomass, in fact, is the aggregate of what comes out after you have managed your nitrogen, phosphorus, land, water, biodiversity boundaries. So it's more of an aggregate sub-cluster rather than a boundary in itself. So that's how we've gone about this in 2 rounds, in fact. And as I mentioned, there's an update now being in review. N. De Silva writes, the climate is rapidly changing as a result of new business and technological development globally. the direct benefits of the new businesses and technological developments go to the rich countries, but the direct impact of the climate change is for poor countries also. How can rich countries contribute to balance this situation? This is a very good question. To begin with, I would even reinforce it further that in fact the brunt of impacts are felt primarily by poor countries. So it's an incredibly inequitable and immoral situation where the subsidy the planet gives is predominantly benefiting the rich countries, and the invoices that are starting to be sent back are predominantly hitting vulnerable, poor, tropical nations in the world. Because it just so happens that developing countries are predominantly in the tropics, and the tropics are predominantly inherently more variable in terms of environmental conditions, and therefore the reinforcement by climate change is harder. This is, I would argue, the heart of the ethical dilemma with climate change, that the rich nations in the world have a disproportionately large responsibility to solve the problem in two ways. One is to transition into a decarbonized economy much faster, to give some leeway and room for developing countries to actually increase emissions over a period as long as fossil energy systems remain slightly cheaper than renewables. And then the second responsibility to transfer technology and funds to enable developing countries to both adapt to unavoidable change, but also to transition into a low carbon future that still delivers on development and well-being. So this is one reason why, as you know, the climate negotiations are stalling, because of this inequity situation. Gregorio Puello writes, do you really think that the human population growth trend will level by 2100, as Sachs says, around 11 billion humans? Will our planet resist that burden? To begin with, I'm totally convinced that we will be leveling off. And that is actually quite robust science. Demography is a very precise, statistically based analysis. And the reason for it to be so, it's probably the only area where predictions actually work. And the reason for that is that for the next 2-3 generations, you know, we have such a good picture of the two variables that matter for population growth. One is the average number of children born per woman, and that has gone down, as you know. It's actually at 2 averaged in the world. Can you believe it? We're down to an average of 2 children per woman in the world. And the second parameter is, of course, longevity. You know, how long time do we live before we die? And because we have such a good grasp of these two parameters, and because they change incrementally, we actually can say with quite good degree of certainty where we'll be ending up. And we know that the demographic transition has already been accomplished. In fact, the bulk of the world's nations are already, you know, have already passed the peak with regards to the imbalance, meaning the imbalance of too many children per woman as compared to longevity. The reason why the population still grows is that there is an enormous inertia in the system, meaning that there's no balance yet. We are giving birth to less kids, yes, but because we're living so much longer at such a rapid pace, because of the fantastic advancements in healthcare, we're still growing. That's the reason. But you know, North America won't be growing. Latin America is barely growing. Europe is not growing. Central Asia is not. Central Europe is not growing. Including Russia. What is growing is Africa and Asia, and that's where we'll see another billion, or potentially 2 billion in Africa, and another billion, or rather 2 billion in Asia. So that's where we have the projection. So I'm quite optimistic there. In fact, I agree with Jeff. Will the planet resist that burden? Well, that's a very, very important question, because it depends on affluence. It depends on our lifestyles. If we have 11 billion people multiplied by an average European lifestyle, I would argue no, the planet cannot resist that. If we have 11 billion people where we have a shift in lifestyles and values, where we actually reduce our footprint by 30, 40, 50%, still aiming for good human well-being, while transitioning into a innovation-based circular economy that is entirely based on renewable energy systems, I think we can do it. I certainly think we can do it. The beauty is that the transition to renewable energy future is within grasp. That is a very, very positive signal. But we will only succeed if we put in place massive regulatory frameworks of a global carbon price and legally binding emission targets for every nation in the world. And whether we like it or not, all nations will have to join. That's a necessity. So even if developing countries, even if poor nations delay a bit, everyone ultimately needs to be decarbonized. And the beauty is that all evidence shows that that's a much, much more desired future. It's a cooler, techier, quieter, more democracy-based, attractive future for humanity. Then let's see here. I'll take Carlos Sonko about the limits to growth in low-income countries. What policies and strategies must be implemented to solve the problems of depletion of natural resources, biodiversity in brackets, aggravates problems of poverty? Now, that's a very complicated question, and I would argue in the following way, that up until recently, again, I use the breakpoint end of the 1980s. We must simply admit, I mean, I know that the following is very provocative, but we must admit that the old business as usual, the old unsustainable model actually delivered. It actually worked. It actually was a phenomenally efficient engine to rapidly improve human wealth, human well-being, through unsustainable growth. And this worked only because there was, space in the atmosphere, there was space in the stratosphere, there was ample biodiversity, there was land to convert, forests to convert agriculture, there was ample fish resources. We could simply push negative impacts, and that was a subsidy, a real subsidy to our economic growth. Now, so that is why poor countries look at developed countries and say, well, you've had your party, don't say the party is over, now we want our party. And that's a very, very logical and position one has to respect 100%. The drama is that since 1990, the model has come to an end. It doesn't work any longer. It creates so much unwanted impacts in terms of health, in terms of cost, in terms of volatility. I mean, just look at the Arab Spring, where food riots preceded the Arab Spring because of oil price volatility, phosphorus price volatility, droughts in Australia, incredible forest fires in Russia. All the damage caused by global environmental change, which is actually undermining the delivery of human well-being if we continue in an unsustainable mode. So, the bitter pill we all must now swallow is that we are in the Anthropocene. And therefore, sustainability is the only growth model for the future, for everyone. There is some wiggling room on the short term, I would argue, on the carbon budget, on fresh water, on phosphorus and nitrogen for developing countries. That's why I argue for an ethically based redistribution of resources in the world, where the rich nations must give space to the poor nations over a transition period. But ultimately, we're all bound towards a sustainable future. We need all sustainable development. I think that's key. Okay, I only have a few minutes here, but then Camilo Ponto I would take here. Okay, do you think that planetary boundaries are a strong argument to change cultural and ancestral practices that are considered a bottleneck for promoting sustainable development? Yes. I at least, well, I'm making my own take on this very good question, but I see the signs of changes in values, of recognizing the need for reconnecting our cultures to nature, our cultures to the biosphere, not in an esoteric way, not in a sentimental way, but in a very anthropocentric, pragmatic way. When the Dalai Lama when the Pope starts actually raising the question that we humans are now potentially destroying creation, and what right do we have to undermine Mother Earth? These are strong signals that we are coming to a point where we can actually also change value systems, where a younger generation and many different cultures in the world are starting to see that we need to have a new relationship between world and earth. Of course, it's going too slow. Of course, it's only fragmented. But, again, coming back to my first point, are we seeing the kernels of a social tipping point? I think yes. I think we're starting to see the kernels of a transition where we see sustainability not only, I'm putting it harshly here, not only as a strategy to protect nature and, reduce impacts on the environment, but as the very vehicle for a desired human prosperous future. That this is the way we can secure development in the future. And this is a change. You see a change in the World Bank, you see a change in the IMF, you see a change in you saw perhaps that Pentagon released another report yesterday showing that global environmental change is a key preoccupation in their priorities for military investments in the world. We're starting to see sustainability not being only the responsibility of the ministers for the environment, but being much, much more an issue for heads of state, for CEOs and big companies, and for communities at large. So, I'm in that sense actually quite optimistic that kind of boundary thinking is slowly but surely eating itself into our kind of deeper mindsets. Shiv, I think, and Matt, I think I'll have to stop there. Over to you.
Thank you, Johan. You can just close the broadcast on Google Hangouts, and we'll close the call.
Okay, thanks. I hope that came across okay.
That did. Thank you so much.
Okay, thanks. Bye.